Good morning, everyone. So this week you guys are working on the lab, the online lab, to give me on Monday. And this Monday we have a lab, like a real lab, and we are going to explore the notions of density and fluid and buoyant force, which is an application of what we learn in Newton's law in case we have objects floating and you consider the environment the, the objects happen to be floating. So what I will do today is to go over um, the book chapters and sections that I would like to to read before class. And so chapter 9. So basically there are three basic states of matter: water, liquid, air, and then you have molecules up in the air like nitrogen. We have oxygen. Our atmosphere is primarily nitrogen, but we couldn't survive without the oxygen in there. You might have heard about carbon dioxide in the atmosphere, and so that is the gas state of matter. And you have the solid one that we have been um, applied and used in all our courses, right? Now, the main concept that we start this chapter is the concept or the quantity named density. So density is a quantity given by the ratio between the mass of an object and then the system of unities we have. Um, uh, the mass is given in kilograms, and volume. This is not velocity, it's volume. And the unity of it is cubic meters. So this table 9.1 gives you the tabulated densities of certain objects. So in solving problems, you might need perhaps to come back to this table and read out these values. Okay. Now, I don't know if you have had the opportunity of dive into a pool and be underwater, and not only that, but had gone uh, 3 feet or 6 feet down. That's even more impressive. And then you might feel some force that is being exerted on your body, especially on your earplugs. Um, and so this is help us to introduce pressure. And in classroom Monday, I introduced the concept of pressures using the concept of impulse and momentum um, by drawing in a board. Let me show you what I did. So remember, there was a ball with a given velocity that hits the wall and then returns back with a final velocity. Remember that? And then I remind you about, let's give numbers because it might be easier that way. So we have velocity 10 meters per second, and the ball rebounds back with, just to make it simple, with the same velocity as far as speed is concerned, but with a negative direction, which means the velocity, remember, is not only the number, but is also direction. So the second situation, the ball is returning and has an orientation of its velocity which opposes the initial one. So if we recall the concept of momentum as being mass times velocity, and just for the sake of for the sake of calculation, let's give 1 kilogram mass. The momentum of this ball, at least the initial momentum, is given by 1 times 10, and the initial momentum is 10 plus, don't forget the sign, kilograms meters per second in I-hat direction. And if you do the same exercise for the final momentum, you're gonna find it to be 10 kilograms meters per second in the I-hat direction, meaning that change in momentum is given by final momentum minus initial momentum, that is negative 10, let me drop the unities for now, minus plus 10, that is negative 20 kilograms meters per second I-hat direction. So we have the change in momentum, and when we studied the concept of impulse, we found that impulse is equivalent to the change in momentum. It's also equivalent to the product between force by the time in which interaction took place, like the ball hit the wall but it didn't rebound instantaneously. There was a small amount of time, let's say 10 to minus 2 seconds or 10 to minus 3 seconds or so, in which interaction between ball and the wall was taking place. Therefore, we can calculate our average force if you just plug information you have. Negative 20 kilograms meters per second, which is your change in momentum, is also, according to impulse, equal to force times a quantity, which is time. Time is always positive in our universe. Then you have a force that is the negative of 20 divided by a certain time, let's say 10 to minus 2 seconds, and then you have a value of force. So this force, in fact, is to the left, right? It's to the left, and it's like the wall giving a big blow on the ball and force it to change its direction and go back in the negative I-hat direction with a velocity of negative 10 meters per second. Okay, so there was an external force acting on it. Now, why does this have anything to do with pressure? Well, if you take now, oops, I don't know what I did here. There you go. If you now think about a container, and you don't have just a big ball, 1 kilogram, but you have zillions, infinite amount, not infinite, but you have some tons of, not tons, but several, not several, more than several molecules of air or water or some fluid that is not solid. So all of them are moving, right? They have electronic interactions among them, but they move all over the place, and eventually they bounce back in the wall, and as a result, every single time they bounce back, there is a force exerted by the wall on the fluid, right? And altogether, when you add up all these forces in a given level, we can talk about a force that is being acted on a certain unity of the area, and we can talk about pressure. So when we deal with fluids or air or water, rather than talk about forces, we talk more about pressure, because it's better makes a better use of force in an object that is extended, that is not concentrated in a kind of a solid uh, confinement. Okay. Take a look at this simulation, which is pretty cool. So we have no pressure, right? Pressure is zero, the pressure inside. We have zero temperature. We have a thermometer in there. So I'm gonna pump something here. See the pressure start increasing a little bit. Every time these little balls hit the wall in average, if you think there is a unique pressure in this container, right? If you think there is a unique pressure in there, every time these little balls hit the wall, it's the equivalent of somebody trying to hold this wall in place and not move as because of momentum, remember that, as the little balls hit it. But let's say we increase the number of little balls in there. Let's just have fun. Now, the average speed of these little balls can be translated into a scale in temperature, and we are going to see that. So the thermometer is measuring a quantity of that can be associated with energy of these molecules as they move, as kinetic energy, as we saw before. But see, eventually the pressure is going to stabilize because I'm not adding more content in there. I can add some light molecules. It's pretty cool, huh? And now they are becoming uniform. So after a while, you see, once this is one of the properties of fluids. Once you release them in an environment, they have the tendency of occupy equally all spaces. Okay. So here is a different situation. You have a cube that you put inside the water, right? Now think about it. The water has molecules, has water molecules, and in the external surface of this cube, these water molecules are bouncing back and forth, back and forth, back and forth, exerting some external pressure on this cube, as if the cube itself, the wall, were subjected to an external force, and the wall itself were trying to hold on as if it were a spring, right? So that if the system is in equilibrium, this external force is being held in place, or is the net force in the wall is zero, based on the fact the system is in equilibrium if the inside material of that cube, it could be molecules, could be air, could be a solid material, is matching these external forces. So the internal force in the cube match the external force exerted by the water, and the system is in equilibrium. Definition of pressure as being the ratio between force and area. That force is applied. This is the crazy professor. And then you have few problems, and I would do lots of problems Monday besides the laboratory. We're gonna have a quick laboratory, and then I will come up with the problems for you. So this section 9.3, let's jump for now, so we don't worry about it. think it's easier if I go this way. 9.4. Okay, let's go to 9.4. Variations of pressure with height. Okay, so here is some solid inside or immersed in a liquid that has an upward pressure on top, which is the equivalent to the weight of water above it. So the pressure on top is P1, the pressure on the bottom is P2, because the pressure is at a point that is below this top point, which means there is more water weight on that level. Therefore, the pressure is larger, since the weight of the water is necessarily bigger down here. So it leads to this basic equation. The pressure on an up position of that lower position of that cube is equal to the pressure above plus the density of the water times the gravity, G 9.8, and the vertical distance between those 2 points. This is a basic one, okay? And then there are problems we are going to resolve. For instance, if this is air, it has a certain pressure. At sea level is the atmospheric pressure. Now, if you want to find pressure at point P1, what that might be? Well, it is equal to the pressure at sea level, P naught, plus rho, the density of this oil, times G 9.8 times H1. And the atmospheric pressure is this value, 1.01125 Pascal unity of pressure. And if you want to find pressure even at a lower level, where you have water in there, so the pressure here is going to be the pressure P1 you just calculated, plus the density of water times 9.8 times this H2. Okay. Buoyant force. Our lab on Monday is going to be based on buoyant force. So buoyant force is this. If you place an object inside a fluid, these objects will experience an upward force, kind of a floating force, that is equal to the weight of the displaced material. Like when you go to the tub and you enter in the tub, as soon as you get in there, so your body feels some space, of course, because you have mass, right? So your body feels some space, and you expel water away. That's why the water level in the tub rises up. Sometimes if it's too full, it's going to overflow. So so what is the weight of the water that has been displaced by the presence of your body in the water? So if you can find that weight, then you know the buoyant force. Like we are immersed in air, right? Because you breathe air. So your body has a certain volume and occupies certain volume inside or in the air. So what is the weight of air that has been displaced by your body? It's not a lot, right? But it's not zero. So you do have some weight, which means the atmosphere kind of levitate us, make us lighter because of buoyant force. Since if you go to the top of the mountain, the buoyant force is less because it has less air in there. The weight of the air is less, meaning you levitate less the buoyant force up in the mountain is less than it is down here. Meaning, if you have a scale and you put something on the scale here, down here, the weight, the scale, if it's a super precise scale, the weight that's going to be measured is going to be less than it is up in the mountain. Since up in the mountain, I mean, you have certain amount of gold, right? And you put in a very precise scale here. But right here, the pressure is high. So we have a lot of air. So this gold is taking certain not negligible amount of air out of space in order to fill the space so that it can place on top of the scale. So when that's done, there is a buoyant force that will diminish the force exerted on the scale that gives you a reading. So when the scale is put up in the mountain, the buoyant force is less, which means the measured weight of the gold is larger. So if you want to do business in gold, go to the mountains, not down here. Archimedes' principle is going to be crucial in order to calculate problems that involves floating, and this is what I will be tackling the most this coming Monday. Okay, so and that's it.